Hello everybody, my name is Matthew Godat and welcome to my Lab 4 physics video. The purpose of this lab is to use Newton's laws and the energy principle to investigate the motion of a spring system in both a computational and real model, and then to compare these two models. The principles we'll be using are Newton's second law and the energy principle, and the discovery we will make is that the total energy remains constant throughout the entire experiment and is zero, as seen in this graph below. So the experiment, a video of a mass with a weight of 0.402 kilograms attached to a spring was analyzed in a tracker software tracking the mass in every time frame, and this gives us position over time data. And then we're able to convert this position over time data into energy data. Our system here is the mass, spring, and earth, which allows us to have no outside forces interacting and the work to remain constant, and the surroundings are nothing. For the initial condition, the mass is pulled to give the system just some movement. Here's a screenshot of the tracker software, and you can see the points being tracked along the mass's trajectory, and then the graph that results. Moving on to the code, using a given starter code, the experimental data is inserted into the glow script code to run alongside the computational model. From the experiment, we need to extract the oscillation period, spring stiffness, and relaxed spring length. And the first of these, the oscillation period, is the average time between the peaks of the graph shown in the previous slide, and this equates to 1.5 seconds. The spring stiffness can be solved for using this equation here. K is equal to 4 pi squared over t squared, where t is the oscillation period, and that gives us 6.8. And the relaxed spring length is negative k, or just using the standard spring force formula, negative k, L minus L naught times L hat, and that gives us, we can solve out of that 0.12 meters as the relaxed spring length. So we then input these constants into the code as seen in this section here. Moving on to the while loop, which is probably the most important part of the code, we change the energy per time step using this formulas here. So here are some screenshots of the code output. We can see that we have the spring with the blue mass, which is our computational model, and that paints this blue trajectory, and then the red ball is our experiment. I apologize for there being no video, but I can't really do that on slides. So our output from this, we get a position versus time graph for the x and y, where the red line is our experiment and the blue line our code, and then an energy change graph. So we have a slight discrepancy in our location data over time comparing the experiment and code, and this is likely just due to some computational error and the fact that in reality the experimental system has drag working on it. Another possible point of human error is placing points inside the tracker software that could be slightly inaccurate. And finally, the questions. Was the energy principle satisfied? Yes. There was no change in the energy of the system as there was no external forces acting on the system, of course neglecting the air resistance in our experiment. You can see this in this graph here where our delta E, the change in energy, is flat at 0. The second question, the oscillation period comparison. Both of the oscillation periods are obtained using the previous method, taking the average of the individual oscillation periods. So for the x direction, the period of our oscillation is 1.66 seconds, and in the y direction, it's 1.52. So these two oscillation periods are different and will give us different constants to solve for. Thank you for listening, and I hope you enjoyed.